Welcome to Physics Can Be Fun with me, Stephen Thomas. Today I'm talking about energy, and in particular, forces. What's the relationship between force and energy? Well, first of all, what is energy? Well, we live in a world that is fixated with energy. We've got the energy crisis, we've got global warming, we need energy to drive our cars, we need energy in all our appliances, we have energy coming from our TV set, there's light energy, we eat food, that's chemical potential energy, we run, that's kinetic energy, we lift things, that is potential energy or gravitational potential energy, we have a stick of dynamite, that's chemical potential energy. So all the things in the world, anything we want to do, we do with energy. Now in this section, we're going to confine ourselves mostly to making things go faster, that is kinetic energy, or lifting things up, that is, we talk about potential energy or gravitational potential energy. So those are the two things that we're particularly interested in this section. And we may be a little bit interested in friction. So some of the energy can get wasted in friction. Now, to make things go faster, and to make things go up slopes, we need a force. And people that are very much cleverer than me have discovered that if you have a force, and if it acts over a distance, then a certain amount of work is done. And work and energy are very similar. Energy is that which has the ability to do work. They have the same unit, which is the joule. So basically, when we are talking about work done, we're also talking about energy. We've either given something energy or taken energy from it in doing work to it, or it doing work to us. So anyway, the point is that if you have a force acting over a distance, it does work. So what are our units? Capital W for work, capital F for force, and delta X for our distance or displacement. Now, just a few things of interest. Force is a vector. Displacement is a vector. A vector times a vector equals a scalar. Work or energy has no direction. We don't have to specify a direction. So it's just has a magnitude or a certain quantity. Right. Now, have a look at what we've got here. We have got a little radio-controlled helicopter. I'm going to switch it on at the base here. And you'll see it's on by its little flashing light. It had a little rotor, but we took that off because we don't want anything but this propeller. We're going to put it on a little car like this. And we're going to use our car and our force, which this is going to create. Now I've switched that on. You see that I can control it, and this produces a fixed amount of force. So watch what a force can do. It can make this car go faster. And there is a force, namely this propeller, causing a car to go faster. So what happened to the energy? It went into making the car go faster, which we call kinetic energy. I could take this board, I could lift it up with two matchboxes, and I could see if we can use a force to make our car climb this board. Let's switch it on and see. Do you see how we could get this force to make something go higher? I'll just do that again. So there's the angle of our board, which you can see. It's resting on some matchboxes. And when we switch our helicopter blade on, our car is able to go up the slope. So that would be an increase in potential energy. It's the same thing as lifting it, but we're doing it gradually over a slope. So we could give it potential energy by lifting it, or we could give it kinetic energy by making it go faster. In this case, it's actually going faster, so it's got some kinetic energy, and it's also going higher, so it's got some potential energy. Now, this kinetic and potential energy we call mechanical energy. Those are the two types of energy which we are particularly interested in. So, now, let me show you something else. Look at this formula. Work done equals force times the distance or the displacement. Nice and easy. If we've got this force and our car goes a certain distance, we say the force which this produces, which is a forward pulling force by pushing the air back. So there's a force forward and it acts over our distance, so we take whatever that measured force is times whatever our distance is, that distance times that force, and we would be able to calculate the amount of work which this little machine is doing. Now that's all very well and good, but what if we do the following? Now notice that this could be rotated. You see how I can rotate this? So that it doesn't point entirely forward, it points a little to the side like that. Now the wheels will only allow the car to go forward, but we now have our force a little bit offset. Watch what happens. There's a force that is both pulling it sideways and pulling it forwards. So let's do that again. I have taken it, there would be straightforward, and I've rotated a little bit, and do you see that it still goes forward, but there's actually slightly less force in this direction. Now if I had to turn it entirely sideways, all the force would be to trying to topple it over. Let's just see. And all it does is wants to topple the car over, but the car will not go. In fact, let me put the car like that. No, that's not going to work. We have to have our wheels will determine the direction, and if we have our force in at 90 degrees, all it wants to do is topple the car. So that is this formula here. Now let's explain what we mean by that. If we have the force at a slight angle, now that slight angle we call theta. So theta is this Greek symbol here. So do you see that our car can only run forward because its wheels and cannot turn? But if we have the force slightly to the side, there is slightly less force in its displacement direction. And if we try and turn the force at 90 degrees, there's no force wanting to pull it forward. So what these clever people have found is if you want to find how much of this force, so if you say have your propeller and you turn it at an angle, that angle theta. So we've turned our propeller from being forward to at an angle theta. These clever scientists have discovered that if you want to find out how much of this force is pulling in this direction, you use the formula that force times cos theta equals that force. We could call this force net, for want of a better word. And we could call that force of the propeller. So the force net is actually the force that is going to drive it forward. And force net is going to be equal to force of the prop times cos theta. The force of the prop times cos theta. Now we can try and prove that to you. If we have a right angle triangle like that, and this is theta, right? This is your hypotenuse, This is your adjacent side, and this is your opposite side. Now, cos theta, or cos, is defined as your adjacent over your hypotenuse. That one over that one. And let's suppose we want to find what that force is. A is therefore going to be equal to, if we cross multiply, A, or in fact what we do is multiply both sides by H. That H cancels out with that, and we're left with A equals H cos theta. So A equals H times cos theta. So this force is equal to that force, which is the hypotenuse, times cos theta. So H, where H is actually equal to the force of the propeller. So the force of the propeller times cos theta is equal to the force net. Is equal to our force net. So this force net is equal to that force times cos theta. So that's just a little bit of maths to show you where they get the idea that force times distance times cos theta is the same as work, which is the same as that. But the difference between these two formulae is if you have your force at an angle, you cannot use that formula. You have to use the slightly more complicated one. All you need to know is the angle of the force from the displacement, which is theta, and then you plug in your values. You look up cos theta multiplied by the force multiplied by the distance, and you get the amount of work done. So you can't just say force times distance. In this case, you've got to say force times distance times cos theta, meaning only the part of the force, this force, that is in the direction that we actually displace. So there we go with how we work out the amount of work which is done.